Greetings, everyone. I am Prakash CHHAPOLIA, Senior Data Analyst and Project Manager at Elite Labs India Private Limited. As I will be presenting a paper on how AI and ML techniques can be used to identify pipeline features and improve the process efficiency. Before starting, I would like to thank you, PINCON, and its organizers for accepting a paper and giving us an opportunity to present the solution on a global platform. I would also like to thank you, my team members, Varun Nidhi, Ravi Sharma, Sudeep Yadav, and all the people who have played an instrumental role in designing the solution. The topics that we shall be covering today is why pegging, what is the need of pegging in the pipeline industry. We shall have an overview of the pegging process and the MFL technology, how we manually analyze to detect the pipeline features, and how AI and ML process can be used to process the pegging data. Lastly, we would discuss the benefits of the AI over the manual process. We know the pipelines are the most cost effective and safest mode of transporting oil and gas. Pipes are made of ferrous materials and are mostly underground, which also means it is prone to corrosion both internally as well as externally due to presence of chemicals in the soil as well as the product being transported, like water, hydrogen sulfide, carbon dioxide, bacteria. Corrosion reduces the lifespan of the pipeline. Operators cannot push the liquid over high pressure, resulting in the failure of the pipeline and loss of product. It is thus important to maintain the pipeline integrity, and operators need to do the pegging operations from time to time. In pegging process, a peg is launched from a launcher station. The peg travels throughout the stretch of the pipeline along with the flow of the liquid and is received at the receiving station. The peg is taken out at the receiver station and the data is downloaded and then analyzed. Pegs are generally of three technologies, which is magnetic flux leakage, also known as MFL, ultrasonic transducer or UT, and electromagnetic acoustic transducer or EMAT technologies. MFL is the oldest and most widely used ILI technology. MFL pegs have powerful magnets and multiple Hall effect sensors installed between the magnets. It works on the principle of physics where the pipe material is magnetized beyond the saturation level. When a feature is encountered, the flux leakage is detected or captured by the Hall effect sensors and saved in a local storage. The data captured from the flux leakage forms a pattern which is specific to a feature, also known as feature signatures. On receiving the data, on receiving the peg, all data is downloaded and then analyzed for the features and corrosions. The data downloaded from the peg are in terms of hundreds of GBs. The data are recorded in multiple bin files and is distributed to a team of 10 to 12 operators. They go through the complete data set and analyze the flux signatures and the grayscale images from the MFL signals. And the features are noted down in Excel sheets. The data downloaded from the peg is in terms of hundreds of GBs. The data is recorded in multiple binary files and is distributed to a team of operators of 10 to 12 people. They go through the complete data and analyze the flux signatures and the grayscale pipe images and note down the location and sizing in an Excel file. A final file of all CD is compiled, which is equivalent to the pipe tally. Manual process has its own limitations, like high analysis time, human biasing, features getting missed, and many more. When we talk about AI, artificial intelligence is a division of computer science in which computers are trained to work like human brain. It makes possible for computers to take decisions based on the data like a human brain does. So machines are trained to identify different features including corrosions. Features with high prevalence like welds, corrosions, sleeves, flanges can be detected using AI. Features with low prevalences are initially detected using a rule-based approach, and when we have a good quantity is being moved to a AI approach. Here we can see that AI model, we have two images, one representing AI model and the other representing a human neuron cell. An AI model is a multi-layered approach consisting of a convolution and pooling layer, which actually acts as a future feature or properties generation layer for the input image. The properties generated are passed to a dense network consisting of multiple interconnected neurons, which then gives a classification of the features. The neurons in the AI model acts exactly as the neurons in the human brain, where there are different dendrites in the human cell, which collects the information from different dendrites, does an analysis, and then we have a synapse which takes a decision and then provides the output on the axial terminal. Similarly, in the AI model, the neurons, individual neurons, captures the data. Individual neurons are interconnected to each other based on the features generated from the pooling and convolution and pooling layers. Different features are then classified and an output is being given either as weld, sleeve, flange, or a metal loss. The AI also needs to be trained just like a human brain. So the first step to do AI modeling is a collection of data and understanding of the data. For this, the client has provided us bin file along with a list of verified features of the data that we have used in the training. The data from the pig contains information collected from the Hall effect sensors, odometers, gyro, sanity, and other sensors. All the data are extracted individually from the binary files, decoded from hex to the desired format. Like for Hall effect sensors, the hex data are converted to MFL signals. For odometers, the hex data is converted to odometer signals, and so on. Once the data is extracted, the required data is then moved to a denoising sequencing. The data captured from the pig is while the pig is in motion. That means there is some induced noise in the data itself. The noise could be because of the electronic itself or the external factors like ununiform pipe material, vibration of the pig, or sensor liftoff. The data is captured while the pig is in motion, which means there would be induced noise in the data. The noise could be because of the electronic itself or the external factors like ununiform pipeline material, vibration of the pig, or due to sensor liftoff. To remove the noise, techniques were developed based on hardware electronics methods, which includes development of low pass, high pass, and wavelet filters. Once the data is moved, processed through different layers of filters, we have filtered and smoothened data, which can also be seen in the coming slide in form of images. So this is a image of the raw data where we can see where we cannot identify the type of pipeline, even any features, if they are present in this section of the pipe. Once we have done the filtering of the data, we can see it's a spiral pipe with some features present on the pipe itself, and similarly in the heat map as well. A smoothened image is more clear with respect to the features of the pipeline. The features needs to be trained in the model so that model can identify and classify those features. For this, the client had already provided us a verified feature sheet. The sheet had a ample amount of data for welds, sleeves, and other features, but was having a limited quantity in terms of corrosion and metal loss. To For AI to work, we needed a very good quantity of features so that the results would be good. So we developed a technique which worked on the real defects, and using the technique, we created many virtual defects in terms of hundred thousands of virtual defects. These virtual defects were used for training the model. 80% of the virtual defects was used for training the model, and 20% was used for testing the model. Once the model was trained and a testing was done on the 20% of the data, the results were analyzed by the operators manually, both in grayscale as well as in signals. Initial results had a high prevalence of false positives, true, true positives, false negatives, and true negatives. The verified data, the feedback from the operators was captured, and then it was augmented to the training data and the model was retrained. With continuous monitoring and feedback, we were able to achieve a very good efficiency, detect 95% of the metal losses in the complete run, and reduce considerable amount of false positive, thus increasing the accuracy of the model. This is a sample output from the AI model where we can see different features along with its location, log distance, and the characteristics of the features. The individual features can also be verified in form of images where we can see proper annotations respect to the features both in grayscale and heat map. The same can be viewed in the smoothened image as well, which really helps the operator to cross-verify the results of the AI engine. When we talk about the reporting module of the AI engine, it has numerous reports, both graphical as well as tubular. The engine supports multiple pic sizes, right from 12-inch to 48 inches, and the reports can be exported into different formats. The operators can directly pull out different reports once the analysis is done. Reports like pipe tally reports, location information sheets, list of anomalies and components, metal loss distribution, percentage wall loss, etc., and many more can be generated. This is a sample pipe tally report from the system where the operator can directly generate the report, give it to the field team or the pipeline division to verify the features or for record purpose. The pipe tally is almost to the PO specifications and meets most of the requirements. When we talk about benefits of AI over manual process, there are numerous. Just to summarize, the AI process reduces human dependencies. That means it reduces retention, monitoring, as well as the training process of the human. It is able to detect small defects which are generally missed during human analysis. It helps in corrosion growth profiling, which provides insights on effectiveness of corrosion mitigation measures. The AI engine provides a better, quicker, and faster results than a human analysis process. This is just not the end of AI on pegging, but to say so far, this is the end of presentation. I sincerely thank everyone for your interest and attention during the presentation. You may kindly share your queries or reach us anytime on our email given on the second slide. Thank you.